What we're talking about now is called numerical integration. Even though we could do this with functions that we know how to integrate, it's a waste of time because we can find the exact area. So why would we find an approximation when we can find the exact area? But I'm going to demonstrate the process with a function that we know how to integrate. So that's why I'm just going to do an example of each of these separately. Okay, we're going to find an integral from 1 to 7 of x squared dx. Obviously, really simple to do. You should go ahead and evaluate this by realizing that this is 1/3 x cubed evaluated from 1 to 7, which is going to be 1/3 times 7 cubed minus 1/3 times 1 cubed. All right. 7 cubed is 343. 343. So that gives us 343 over 3 minus 1 over 3. And therefore, my exact area is 342 over 3. Which is approximately equal to 100. Actually, it's not approximately equal to, it's exactly equal to 116, 114, 114. Okay. So what you should realize is we have just calculated the exact area. So I'm picking this for a reason so we can actually make a comparison by using the 3 different approximation techniques that are most beneficial. And we're going to start off with the midpoint rule. So we're going to start with the midpoint, with midpoints here. So all right, so the first thing we're going to do is we're going to create a graph of this. Okay. And on this graph, we're going to plot some values. So we need to make sure that we're going from 1 to 7. So 1, 2, oh, I'm sorry, I should say that we're going to apply these rules where n is equal to 6. Okay, so we're applying the rules where n is equal to 6. So that's why from 1 to 7, we could see that each hash mark is going to be 1 unit away. This won't always be the case because if I said break it up into 5 pieces, you'd have to say, well, from 1 to 7 is a distance of 6. And so each value would be 6/5. Right? But this one right here, I'm making it nice and easy. And here is our graph. Okay. All right. And I'm also going to graph x squared. Okay. Good enough. And now we're breaking it up into 6 individual pieces. So that's why you could see that, first of all, our delta x is equal to b minus a over n. So I made this one nice and easy because 7 minus 1 over 6 is just 1. Okay. All right. So that means that each of these values here should extend from the x-axis straight upwards. Okay, do another one here. Okay. So I'm just going to make this one graph once and then copy it here. Damn it. This is really frustrating. All right, give me a sec. I'll just do it this way. And then finally a partition here. I'm sorry I'm not as neat as when I draw on the board in a classroom, but bear with me here. So I'm going to redraw this one because I don't like it. All right, so basically what we've done here is I've drawn vertical lines, and this is a really important starting point for every one of these graphs. So this graph right here now has 1, 2, 3, or it has 1, 2, 3, 4, 5, 6 different partitions as it was supposed to, right? All right, and let's put this down here somewhere. Okay. So for the midpoint rule, the idea here is that we're going to be picking the midpoints of each one of these in order to act as the height for our triangle or for our rectangle. So the midpoint rule is still using rectangles in order to come up with our values. So we're going to be using this height here, which is at 1/2, this height, which is at, or that's at 3/2, this is at 5/2. This one here is going to be at 7/2. This one's at 9/2. 11/2. And 13/2. So what we got to realize is each of these are now creating the heights of the rectangle. So you can see that part of that is going to be an over approximation, while part of it is going to be an under approximation. So each one of these rectangles is kind of being close anyway, canceling out part of our under and over approximation. So every one of these is just going to act as the height of that rectangle. The midpoint will act as the height of each rectangle. And so you can see that when I'm drawing this, I'm just connecting each partition. Right? And so that's the picture for our midpoint rule. And we should see that each of these has an over approximation and an under, an over and an under, right? And every one of these is close to canceling out. So I'm guessing that the answer to this is probably going to be pretty close to the answer that I got for the exact value, right? So notice that each of these values is going to be using the height at 3/2, the height at 5/2, the height at 7/2, the height at 9/2, 11/2, and 13/2. Cool. And that's why the midpoint rule using 6 rectangles has a formula or a symbol we just call M6. Okay. And notice that all we're doing at this point is taking the width, but notice that the width here of one of these is still going to be delta x. The width doesn't change. The width is still 1. The only difference is now the height is not going to be used at 1 or 2. It's going to be used at each of the midpoints. So that means that I'm going to take delta x times the first height plus delta x times the second height plus delta x times the third height plus delta x times the fourth height, which is really why we factor out the delta x. And all we're doing now is computing our function values at 3/2, 5/2, 7/2, and so on. All right, we all good there? So any questions on the midpoint rule? So this is just, and again, I want to mention that this is a complete waste of time, considering we already know the exact area. The purpose for these numerical integration techniques is for functions that don't have a simple integral, that we don't know how to integrate because it's not an integrable function, or we don't have a rule for it. Okay. Cool. All right, so no issues with the midpoint rule? All right, so now let's take a look at the trapezoidal rule then. Okay. So the trapezoidal rule is now a little bit different because in the midpoint rule, we were using rectangles to approximate that area, but now we're using trapezoids. Okay. And so the trapezoidal rule, I want you to recall what a trapezoid is. So let's draw a trapezoid here. All right, so here's the trapezoid. And you got to realize here that, first of all, I'm going to call this the height. Even though it's on its side, it's basically the height, because no matter where you are throughout this entire figure, this is still going to be the height, right? And this is going to be one base, and this is going to be the other base. So let's try to find the formula for this. So if I wanted to find the formula for the area of this rectangle, well, the area is going to be equal to the area of the rectangle right down here, okay, plus the area of this triangle way up here. So I know that it's going to be the base 1 times the height plus, and now I got to figure out what this length is right up here. So how could I find this length right there, the height of, or the base of that triangle? What would that be?
1/2 B2.
Well, B2, remember, is going to be this entire length, and it may not necessarily be halfway through. So I can't say that it's half of B2.
B2 minus B1?
It's B2 minus this distance right here, right? So it's B2 minus B1. So that's going to have a formula of 1/2 B2 minus B1 times H. Dogs running through the house on the wood floors, just like tapping all over the place. All right. So if I were to now distribute this through, let's go ahead and get another formula for this. So we get B1H, and then over here we get 1/2 B2H, and then we get minus 1/2 B1H. No, that's not B squared H, it's B1, 2. Okay, well, if you take a look at this now, you can see that B1H and 1/2 B1H are like terms. So if I combine those, I get 1/2 B1H. So if I were to simplify this, I get an area formula that's just 1/2 the sum of the two bases times the height. So that's a real similar formula to the area of a triangle, except that I'm now going to say it's 1/2 base 1 plus base 2 times the height. Well, if I look down here now on our graph, let's move this up here. Okay. We should still realize that when creating our trapezoids, what we're really doing now is just looking at each of these heights at f of 1, f of 2, f of 3, f of 4, f of 5, f of 6, and f of 7. And notice that this blue curve is curving. It doesn't look like it's really curving from my picture, but it is. And so if I were to now just connect these two dots, notice that I just keep creating trapezoids that look like they're following the graph pretty closely. And so all we're doing here is finding the area of each of these trapezoids. But notice that the height is going to be the same every time. So all I'm doing is adding a bunch of these heights. So if I wanted to find the formula for T6, which is a trapezoidal rule, okay, we just have to realize that we're taking 1/2 base 1 times base 1 plus base 2 times the height. Well, let's just look at this first one. Isn't this first one going to be 1 or f of 1 plus f of 2? So the first one is going to be f of 1 plus f of 2 times the height. But then I'm going to be adding on the second one, which is going to be f of 2 plus f of 3, because those are the bases, right? So notice that we're going to add another 1/2 times f of 2 plus f of 3 times the height. And we're going to continue this on forever until we get to this last one, which means that we're adding f of 6 plus f of 7 as the heights, which is going to be our last figure. 1/2 times f of 6 plus f of 7 times the height. But if we look at a little more detail here, we should realize that what's really happening is that look at how 1/2 shows up in every one of these. And look at how h shows up in all of these. And look at how h is nothing more than delta x. So the height is delta x every time. So why don't we just take away all of the 1/2 delta x's and factor those out. And now write what's left. So if we see that each of these are actually delta x, then I was able to pull out the 1/2 of the delta x. Any issues so far? But now I want to know what's going on inside. So remember that inside here, each of these heights right up here were the heights of the rectangles at each of the midpoints. Now for the trapezoidal rule, I'm not using the midpoints. I'm actually using the nice simple values of 1, 2, 3, 4, 5, and 6, and 7. Okay, but you should realize something really important here, that f of 1 and f of 7 are only being used one time, right? They're only being used once because it's the height of the first trapezoid, but then that's the only trapezoid that's using f of 1. And then f of 7 is the height of the last trapezoid, or is the base, the right base of the last trapezoid, but it's only being used once. But if you take a look at everything else, look at how f of 2 is being used once here for this trapezoid, but then it's being used a second time here. Because f of 2 is not only the base of this trapezoid, it's also the base of this trapezoid. So every interior x value is going to be used twice, which is why the formula is simply going to be f of the left endpoint plus 2 f of every interior endpoint. And that's why all those interior ones are simply being multiplied by 2. And for the last one, again, it's back to a coefficient of 1. Last semester, I actually did teach you about this in a different way. Anybody remember a different way we ended up finding the use of the trapezoidal rule back when we were learning about left, right, and midpoints? Anybody remember? We actually talked about the trapezoidal rule in Calc 1 a little bit. Nobody remembers how to do that? All right, well, it turned out to just be the average between the left and right hand endpoints. And there's a simple reason, because let's just look at one rectangle here. If I used this as the left endpoints, notice that I'd be using a left endpoint, so this would be the approximation, right? Or if I used the right endpoint, then this would be the approximation. Both of these are pretty poor approximations, but you can see all of this white area here is kind of the extra. So if I were to now just take the endpoints and connect them, notice that I'm basically taking the average between the lower estimate and the higher estimate, which is why the trapezoidal rule is actually just nothing more than the average between the left endpoints and right endpoints. But notice in left-hand endpoints, I'm only using these values. But in right endpoints, now I'm using these values. And notice which ones are used once and which ones are used twice. Notice that 1 and 7 are only used once if I take the average, but each of these are used twice. So that's where the formula is, is a little different as well. Cool. And now for Simpson's rule, I am not going to prove it because it was proven in the video last night and it's a much longer proof. And so I'm not going to do it. So instead, we're just going to discuss the rule and how it works, okay? Simpson's rule can only be used when there are an even number of intervals, okay? So when you end up talking about Simpson's rule, n must be even. Okay, can somebody tell me why that's true? Why does n have to be even? Does anybody, what did you learn from the video? Why is that? Anybody? Okay, well, I hope we're at least trying to watch the videos. That would be really important to make sure of, okay? But because I don't always go over the derivation. What we're essentially doing is now what we're doing is creating quadratics or parabolas that go through each of these points. But notice that it has to be going through 3 points. So notice that this right here would say be my A0 and A1 and A2 and A3 and A4. A5 and A6. But now Simpson's rule, there's a great derivation that shows why this formula works, so I would like you to watch those. But essentially you're trying to find a parabola that goes through each 3 consecutive points here. Okay, and then same thing here, and then same thing here. And notice that that's why you have to have an even amount, because if you didn't, you wouldn't have enough to actually go around. So there has to be each of these middle points here, 2, 4, 6, are all going to be the middle of each of these, are going to be the middle of each of these parabolas. Okay, so if we were to look at Simpson's rule, S6, turns out that unlike the trapezoidal rule that had a coefficient of 1/2, this one has a coefficient of 1/3. Okay. And anybody know what the difference was between Simpson's rule and between the trapezoidal rule and Simpson's rule?
So 2 and 4 alternates?
Yeah, you're gonna have, first of all, you're still gonna have one of each of the endpoints. So you're gonna have f of 1 occur twice. But notice that you're gonna be alternating coefficients of 4 and 2, which is pretty weird or pretty interesting how that showed up. And I encourage you to look at that derivation from the Patrick JMT video. It's pretty cool. But notice that every odd amount starting with the 0 is going to be the first term. Every odd value here will then have a coefficient of 4. Okay. It's about to shut down. So okay, so that means that each of these values of A1, A3, and A5 are going to have 4. So I'm going to have 4 f of 2. But then it's going to be 2 f of 3 plus 4 f of 4 plus 2 f of 5 plus 4 f of 6. But then I get to the end, because now if A0 was the first term and A6 was my last term, you could see at this point that you're only going to be using that once, because it was only part of one of these parabolas. So notice that this was only part of one parabola, and this was only part of one parabola. And so notice that this is going to be plus f of 7. Cool. And there you have it. So any questions there?
What's the advantage? What's the advantage of using Simpson's rule over trapezoidal?
It's a great question, because for most curves, you're not using lines to connect the endpoints. You're actually following the curve a bit better. So even though this one right here, I'm not drawing it very well, so you can't see. You might be like, well, that looks like it's a worse approximation. But if you think about curves, okay, curves go like this. So is it better for us to approximate these with lines, or is it better to approximate them with parabolas? You see, so the idea here is that we're saying I could just connect these 2 points here, or instead I could just pick some point in the middle and create a parabola that more closely follows the curve at that point. And then I could say, okay, well, I could go, with a line, or I could actually follow it more with a curve. Okay, so the purpose of Simpson's rule is just to be able to, since we're dealing mostly with areas under curves, parabolas are curved, so we might as well use a curved approximation as opposed to straight approximations.